I'm talking about ionic and covalent compounds and the definition of both of them right here. For ionic, they steal and lose electrons. They disassociate in water. They come apart, and they dissolve in water as well. They conduct electricity and are metal and non-metal. They're made up of those, and they have high electron negativity difference over 2. And I'll explain later on in the video how you could determine if it's over or lower. They for covalent, they do not conduct electricity. They share electrons. They're made up of non-metal and non-metal, so that's an easy way to figure out immediately if it's covalent. They do not create ions. They dissolve in water and do not dissociate, so they don't come apart. And they have electronegativity lower than 2. So down here in my Bohr model, you can see the K right here transferring its electron, because that's usually what they do. And here they steal or lose, so that means they're losing their valence electron, sending it over to the I over here, so it could be full, because it's already almost about to be completed its shell, which is the ring. So once it transfers over, it's going to be complete, so it's whole, which is the purpose of K, is to lose this one so that one can be complete. Lewis structures usually don't work for them. For ionic, I forgot the main reason why. I don't really remember, to be honest, but here's the Lewis structure for this one. It's transferring over its electron to I, and then its final form, which is this K, and you can see them that they're kind of sharing it, I guess, but they're not supposed to. It's the attraction of ions. So, yeah. I didn't mention this, I forgot to put it over here, but ionic compounds do create ions, so yeah, that's its final form. And here's some more details about what's going on here in the Bohr model. Oh yeah, big flaw of the Bohr model is the higher the element is, I guess, the lower it is down there in the periodic table. The more amount of shells it's gonna have, which is the rings. So it's just gonna keep getting bigger and bigger and bigger. It did have more right here. This one had way more, but I just had to make it smaller for the sake of the video and whatnot. And usually when they transfer, the element that transferred the electron becomes a positive charge, and the one that gained one becomes a negative by 1, respectively. Alright, down here the Lewis structure for H2H4, which is a compound of a covalent compound. The way you set this up is by setting up the one that isn't hydrogen. In this case, we do have hydrogen right here, the H. If it was another element with like CH, or not CH, like CI for sake, then you would just put them down normally. Alright, so first we would put down the N for nitrogen. Connect them first. As you can see, this one, they connected. It doesn't matter at all where or how you set it up at first. Sorry, I'm out of breath, bro. Diabetes is gonna get me. I can see the H right here for the hydrogen. I put them after I connected to both ends. Now you have because hydrogen only has one electron and 1 valence, which is the same thing, and slash shell and whatnot. So they would connect to the N, which has 1, 2, 3, 4, 5, 6, 7, 8. Wait, that doesn't make sense. 1, 2, 3, 4, 5, 6. It would have 3 available ones to be connected, which is this right here. This represents one connection, one bond. and these would be considered lone pairs. So these two are bonded to this one, and this is bonded to that, and then etc. and so on. That's how you technically would set it up. Probably not the best explanation, but the best one I could come up with. You know, the two nitrogens would connect to the blue model or whatnot because they're supposed to. That's what they want to do because they're sharing. They're not like stealing, like, oh, they're not stealing or losing like the ionic ones, for example. So yeah, and this is the 3D model of it. I used the model kit to get this image, and these over here are the leftovers. Oh, you can't see that, but the leftovers. Let me just the leftovers. These are called lone pairs. Those are the ones that could not connect because they couldn't connect to anything. So they're there. You would make this usually on an app, or you could try your best to do it after you get your wedge model. And these over here, these bad boys, these are the wedges and these are dashes. It's the wedge dash model. Forgot that. You usually only know how to tell how to make this after you made your 3D model. It just helps a lot more. It's just easier to tell because as you can see here in the model, this right here is coming at us, and the black right here, the wedge, which is this what I highlighted down here earlier, means that it's going towards us, and the dash, which is this one, means that it's going away from us. Just like this one. This one's kind of going away. This one's kind of going away. You can see. You see that? It applies here. So this is just basically a model representing what happened over here. It's its own separate thing. And it's a triagonal bipyramid. You could figure this out through a Vesper model, like by knowing how many bonds it has and how many lone pairs it has. And depending on that, you could figure out how many and whatnot. Here's I told you guys earlier, I don't think I did on this video, I'm not sure, but that I was going to tell you how to get the electronegativity. So, for example, I will use my N2H3, and N is nitrogen, which is over here, and hydrogen. As you can see, it's 2.1 and then 3 point. You would do this by subtracting the greater one to the lower one, so it would be 3.0 minus 2.1, and what you would get would be 0.9. I did this beforehand, so it's just easier to show you, but I just wanted to show you how you would do it. And using the electronegativity like this on a chart, it's an electronegativity chart, it will just help you a lot more in figuring it out. But with that, you could also figure out if it's ionic or covalent. As I told you guys earlier, it's 0.9, which would make it you got it, covalent. And then for the Ki, it would be ionic because it's non-metal and metal. That's why. Ain't that crazy? Ain't that crazy? Yeah, this is basically it. It's probably shorter than most videos. I'm probably out of breath a lot. Gotta work on that weight. So yeah, that's it. That's it for my video. And if you have any more questions, ask down in the comments. I'll try to get to you as best I can. And I guess I'll see you for the next project.